Today, we heard a talk from Paul Downhauer laying out the whole sort of framework of dynamic catalysis and catalysis resonance. And Omar is going to tell us today about an experimental implementation of this idea using electrochemistry. So, Omar, unless you have something else to say for the afternoon, the floor is yours.
All right. Thank you very much, John. Thank you all for coming back and being here and making AdCat a success today. Like John was saying, what I'm going to be talking to you about today is this idea of dynamic catalysis that you heard about from Paul earlier, still related to scaling relations and volcano curves, which Zach touched upon. And I'm going to try to convince you we can make use of this in a dynamic sense for this model system over here with formic acid decomposition to hydrogen and CO2 through electrochemical means. So without belaboring the point, we've heard about this in the last two presentations of why volcano curves exist and scaling relations. But we looked at the earliest case for which we know this kind of behavior exists, which is formic acid decomposition. So here I'm showing you what happens with thermocatalytic systems, where you can decompose your formic acid to either CO2 or CO. And if you look at this experimental data here, taken from the group of Israel Box, and you plot it against the D-band center of a metal as calculated by the Norskov group, you'll see this kind of volcano behavior, which has been frequently reported for this chemistry. And you tend to have platinum up here near the top of the volcano. And generally, it's thought that on the left-hand side of this plot, you're less weakly binding adsorbates in general. On the right-hand side, you're more strongly binding. And this has implications for the rate-determining steps, or if there's a single one exists, and which one might exist on either side of the volcano. And we've seen that the same situation will exist for formic acid electrooxidation. So more or less the same chemistry. We are just using now electrons through applied potential to drive this oxidizing chemistry. And so this is experimental data from Radoslav Azdik at BNL, where you can see that the current also shows similar behavior, this volcanic type behavior. And here you can take current as directly proportional to the turnover frequency of a catalytic system. So our thought here was to take platinum with this model kinetic system and try to see if we can make use of this idea of dynamic catalysis and bouncing back and forth between either side of our volcano curve. Okay, so first things first, how does this chemistry proceed on the surface? You start out by adsorbing your formic acid on the platinum surface. One of the mechanisms that can proceed is through an OH cleavage first, and you have a formate species on the surface, whether monodentate or bidentate, and that releases a proton and an electron from the working electrode going to the counter electrode, where it will recombine to form a hydrogen atom on that surface. And then you can have a second step after that, where the formate undergoes a CH cleavage, another proton, another electron, you ultimately get your CO2 product. Now, alternatively, there's what's called the direct pathway sometimes, which involves this hydroxyl carbonyl intermediate, which starts out by having a CH cleavage happen first, and this rapidly decomposes, hence the direct name, to give you your CO2 desorbing from the surface. So these two pathways just differ in whether you have CH or OH cleavage first, but they're both purely Faradaic in the sense that every elementary step is proposed to involve a proton and an electron being transferred. Now, conversely, on the other side of this, you can have a mixed pathway or an indirect pathway, as it's called, where you started with a non-Faradaic dehydration of formic acid to adsorbed carbon monoxide. So no electrons or protons being transferred, just a thermocatalytic step. And then once you form your adsorbed CO, now the Faradaic chemistry can kick in. You split water, you make an OH on the surface, and that will act as an oxidizing species for the CO to become CO2. So regardless of the pathway that you take here, you're going to end up with the same set of products. CO2, 2 protons, 2 electrons, which will recombine at the counter electrode to make hydrogen eventually. However, the same cannot be said for the relative energetics. So if we look at just their delta E's and their activation energies for the various steps, what I want to bring your attention to is the CO-mediated pathway, which is just this thermodynamic well sitting down all at the bottom. Not surprising when you're dealing with something like platinum, and you have a very strong binding energy for CO. And what's interesting about this pathway is that you can readily make CO from formic acid at room temperature. This has been estimated with experimental measurements to be somewhere on the order of 10 seconds inverse. However, you have a very difficult time, not surprisingly, getting it off the surface because of that high binding energy. So here comes the idea of dynamic catalysis, where can we bounce back and forth between two energetic states, perhaps bouncing back and forth between two applied potentials, one where we facilitate the formation of carbon monoxide and one where we facilitate its removal. So research in this area has mostly focused on, can I make a catalyst that avoids making CO? What we're saying here is, let's lean into that. Let's use the catalyst in the way that it wants to behave and let it make CO and take advantage of that to drive our rate through this indirect path. Okay, so how are we going to do that? Just a quick background on this. We're using an electrochemical cell that's kind of like a CSTR in some sense. So you have a working electrode, which is our platinum catalyst, essentially. We have a counter electrode, which is where your protons and electrons recombine. And then you have a reference electrode, which just makes sure that you're applying the potential you think you are to the working electrode. And you have a purge of nitrogen going in to drive out your CO2 product, so you can detect that with gas chromatography and analyze your rates accurately. And we've put out the details of this in a recent preprint, which I'll have the link for at the end of this presentation, showing you how you can make this a gas-tight setup just using off-the-shelf liquid chromatography fittings. Okay, great. So the first thing we looked at is, how do things operate under steady state or at potential static conditions, where we can measure the turnover frequency here through chemical analysis, not through the current. And what we can do is measure the molar flow rate of CO2 coming out, normalize it by the moles of platinum we know we have available to us, which we estimate based on the surface area of our platinum that's available for catalysis, and an average site density of about 10 to 15 sites per centimeter squared. So once we do that, we see this volcanic type relationship between the turnover frequency and applied potential, where here I have the voltage versus the normal hydrogen electron scale. And this is pretty common for what's reported for this chemistry on platinum. You get a peak somewhere about 0.5 or 0.6 volts NHE. And the reason that happens is still debated somewhat, but generally goes something along the lines of, on one side, I'm increasing my ability to oxidize my species on the left-hand side of this curve, but eventually I'm going to start making a lot of OHs on the surface, and that limits my ability to really keep the rate of reaction going as high as I would like it to go. So what we're going to want to do is oscillate between either side of this volcano to ultimately see if we can exceed what's available to us under steady state conditions. Well, before we do that, we want to confirm that what we're measuring is representative of the electrochemical reaction, because the tricky part is when you apply potential dynamic conditions, you can have a situation where you are constantly oscillating your potential, and your currents could change as a function of something not to do with your reaction itself, but for example, charging or discharging your double layer. So we confirm this by looking at our current versus our extensive rate of reaction multiplied by Faraday's constant. And that should give you a straight line with a slope that's about 2 moles of electrons per mole of CO2. So that's in line with the stoichiometric ratio you would expect. So that's telling us the currents we're measuring are realistic in terms of the rates we are measuring for this reaction. Okay, so that's the static case. Now, if we want to extend this now to a dynamic case, what we're going to do is start out our cycle at open circuit. And what I mean by open circuit, that's a condition where the switch is essentially turned off. There's no potential. There's nothing that can move in a Faradaic sense. And the reason we do that is, if you think of our chemistry pathways, only the formation of CO and the absorption of formic acid can proceed under these conditions. All of the other chemistries are kind of frozen out at this point. And then we can start out by using a square wave to oscillate our potentials, where we instantaneously jump up to 0.8 volts, which was on the other side of the volcano curve, so the right-hand side of the volcano curve. And what we'll see is this sharp increase in the current, which is again indicative of rate. But that sharp spike is very short-lived. And what we think this has to do with, and we're not the first to report this, you're oxidizing your CO off the surface. So you're seeing the electrons are associated with making the hydroxyl species, but then using that hydroxyl species to kick CO off the surface and complete your catalytic cycle. But that's very short-lived because your coverage of CO rapidly runs out and your current falls back down. But we can keep applying multiple cycles and get this same current behavior multiple times in a row. We can define two things here. We can define an average current. So this is the charge that evolves, the area underneath one of these current spikes, and normalize it by the time spent not only applying the potential, but the time at the potential and at open circuit, so time for one cycle. And that gives us an average current to wrap our heads around. And we can also define our frequency as the inverse of the sum of the time spent at both conditions. So let's put this to work. So what I'm showing you here is with time on stream, we're starting out under steady state conditions at 0.8 volts. And then I can instantaneously start to apply the square wave potential. And what we see is a rapid increase in both the turnover frequency measured by gas chromatography and the current as we're measuring by our potentiostat, where we see about an order of magnitude increase by oscillating, as I'm showing you in the cartoon on the left. We can then confirm what's happening here by stopping the oscillation instantaneously again, returning to potentiostatic conditions, and we see that our rate does drop back to the original condition, and the same story for our current. And we've also measured the residence time associated with our reactor, just the hydraulic residence time. And it's very much in line with these transients that you see over here. And ultimately, what we find is that the change in the current is similar to the change in the turnover frequency, telling us that we are, in fact, maintaining this 2 moles of electron per mole of CO2. So that's good to know. Okay, so the next question is, why does this work this way on a deeper level? How can we try to answer this? So we looked at some calculations out there by Mike Janik on this chemistry, where we could see that the non-Faradaic part is not going to be affected by your applied potential, the ability to make CO. But your ability to oxidize it is going to be strongly affected by your applied potential. So at 0 volts, this is the situation. You've got a large barrier, and this 0 volts is essentially the open circuit potential. And then as you keep increasing the applied potential, your barrier decreases and your reaction becomes more and more exergonic. And so to quantify this, you can think about it in terms of this equation over here. Your delta E at any applied potential is equal to some standard state delta E, and it decreases based on the number of moles of electrons you have involved and the applied potential. Generally, you have 1 mole of electron involved. For every volt of applied potential you give, you're going to decrease that delta E by about 100 kilojoules per mole. And then we can relate the barriers to this change in delta E through a BEP type relation, where I have a linear slope of alpha that's in between 0 and 1, depending on my transition state position. And I have an intercept, which is my athermal activation energy. Essentially, what's my EA when my delta E is 0. If I put all of this information together, this is kind of what we see here. So we have a scaling relationship based on the applied potential, where we see that we have a slope of about 1/2 as far as delta E is concerned, which is a pretty typical scenario for catalytic systems in general. And you see that the barrier drops somewhere about 80 to 90 kilojoules per mole for every volt of applied potential that you give your system. So conceptually, what we think is happening over here is that you are absorbing your formic acid, you are then forming CO, and this is the time you spend at open circuit, and then you apply a potential, and that lets you form your oxidizing species, and then you get your CO2 off the surface. So what we want to understand now is this what's happening, and also to be able to tune the time we're spending at both of these conditions to maximize our turnover frequency. So one quick proof I just wanted to show you is that we can do what's called a linear speed voltammetry, where we look at how the current evolving changes as we ramp up the applied potential. So this is like a temperature programmed desorption, but with applied potential. And we get two peaks. The first one at a lower potential associated with the more purely Faradaic pathways, and the second one associated with the CO oxidation of the surface. So if our hypothesis is correct here, what we should see is that as we spend more and more time at open circuit before ramping the potential, you should see peak 1 decrease and peak 2 increase. And that's exactly what we see here as we keep increasing our open circuit time. So it suggests the more you're at open circuit, the more carbon monoxide you build up, the more you will get of this second peak over here. So now putting this all together, we thought of this in two ways. So these are two different potential oscillations, one between physical open circuit, where we turn things off, and one between the applied open circuit potential of 0 volts. For reasons I'm happy to talk about at a later point when there's more time, this 0 volt as a potential is the same as the open circuit. But for hardware reasons, you have better control over the frequency with the red data over here. So focusing on that red data, what we're seeing is anywhere between a frequency of 10 and 100 hertz is where we appear to be maximizing the turnover frequency for this reaction, reaching about a factor of 50x over the steady state rate at 0.8 volts. And this is kind of in line with what we'd expect from the theory of dynamic catalysis Paul was talking about earlier, where I was telling you in the first few slides that CO forms somewhere at about 10 seconds in versus what the experimental measurements tell us from previous liquids. And putting this all together, have we not only exceeded the steady state rate, we're also able to exceed the steady state rate of the volcano peak here by about a factor of 20x by using 100 hertz oscillation between open circuit potential at 0 volts, where no reaction is happening, and 0.8 volts, where you're able to oxidize your CO off the surface. So in conclusion, by kind of understanding what the mechanistic pathways are and leaning into this CO-mediated pathway rather than avoiding it, we can take advantage of a potential dynamic catalytic system, and we can eventually get past what's available to us just under steady state conditions. And so with that, I want to thank everybody that's been involved, my group here at UMass, especially my first two graduate students, Ajibola and Han, who've been responsible for bringing the lab up to speed in under 15 months. And the postdoc that's done all this work, Josh Gopi Singh, along with Sean Burke, as well as our collaborators at the University of Minnesota, Paul Danhauer, Dr. Alex Ardon, and Manish Shetty, and of course the funding agencies as well, the NSF funding this through an EAGER award, and the DOE through the Catalysis Center for Energy Innovation. And this is a link for the preprint I was just telling you about that we managed to get out just before the shutdown forced us to stop working. And if you have any questions, I'll be happy to take them.
All right, thanks a lot. We have a couple of questions here online. The first one that I want to ask is it going to be possible to match the appropriate resonant response for the reaction with the counter electrode? So if, for example, in a fuel cell or in a water splitting reaction, you may not have the same resonance response at the other electrode. So is this going to work when, in that scenario, or is it only appropriate when you have like a counter electrode that's independent of those?
Yeah, that's a great question. So it would come down to what's really limiting you. If the counter electrode is what starts to limit you in any way, yes, you would likely find a different resonant frequency. The situation would likely become more complex. We don't know just yet what would happen. But yes, what we're showing when the working electrode is what's limiting you and independent of how the counter electrode is performing.
All right, the next, maybe the next question is, have you been able to quantify CO coverage versus oscillation frequency, maybe by a stripping charge? And related to another question, how do you account for capacitive charging in the square waves?
Yep, both great questions. So we were in the process of trying to use quartz crystal microbalance, an electrochemical one, but hopefully as soon as we're let back into the lab, we'll be able to do that. Now, how I can answer this is through this linear sweep voltammetry over here. So as you spend more time at open circuit, you are oxidizing more CO, and that's the charge underneath this curve. So you can see the more time you spend at open circuit, the larger is the charge, the area underneath the curve associated with the CO stripping that's happening.
Okay, let's see, I think we probably should transition over to Hong Liang.